Well, hello everyone. My name is Amr Elsayegh, and I'm proud to present to you my project for Dr. Casey Canfield class, Advanced Engineering Management. And my project is called an exploratory and predictive analysis of the price of single-family houses in the US. I know it's a long one, but I'm going to try to explain it as much as possible. So, to give you an outline about what I'm going to talk about today, I'm just going to give a brief background about the project, the goal for this project, how I did the data collection and data cleaning, and then we'll proceed with the data analysis and results by the exploratory data analysis and the predictive models and predictive analysis. And we will end with final and concluding remarks about this project. So for the project background, we are talking about the single family houses, and single family house mean a standalone residential buildings. And as we most people know that the American dream is to have the dream of home ownership. And there are 95 million single family houses in the US as of 2019. The problem is that 66% of renters cannot afford the purchasing price of a house. And it even grows bigger as a problem as the growth of houses prices is nearly the double of the growth in wages. And that calls for a solution for the affordable housing crisis. And that gives the motivation behind working on this project. So for the research goal, my research goal is to study the real estate market behavior by predicting the price of single family houses in the US. For the data collection, so the source was the US Census Bureau, where they conducted a survey, and it was collected by the Survey of Construction, SOC. And the people who filled the survey were basically the builders and owners of single family houses. And the good thing about this data, it's huge. It has nearly 500,000 observation, and it spans from the years 1999 to 2018, so around 30 years period. And in this survey or data, they have all the characteristics of a single family house, meaning the number of stories, number of bedrooms, bathroom, square foot area of the house, square foot area of the lot, what kind of heating system, kind of heating fuel use, foundation, literally everything about the project, the construction project. So that's really nice to be able to study the sales price for this project. So for the data cleaning, we had around 61 variables to start with, but as I go about the project, I found that there are many missing values from the 1999 to 2018, especially the way they made the survey. It was different in the number of variables being used, or even the legend for variables changed. So I removed all variables that has high number of missing values and that also were logically irrelevant to the target variable, which is the sales price. So we ended up with 30 variables that are relevant and do not have missing variables. Also for the sales price variable, we removed all observations that has no sale price. And I also removed sold houses with missing values. So for the exploratory analysis of this project, first thing I did correlation analysis is to make sure that variables are not highly correlated to each other, so that whenever they are included in the regression models, they don't give false values. And as you can see here, the darker the color, either going to red or going to dark blue, that means they are highly correlated. And we can only see 3 instances where they are kind of highly correlated, but the rest are not showing any big problems. And the ones that are highly correlated were not included in the further analysis for the regression models. So I started by doing histograms of the continuous variables that we have. So lot value, sales price, square foot area of the house, square foot area of the lot. And as you can see here, that the histograms are kind of skewed, as we can see that we have single family houses that are very, very expensive, very large in the square foot area, and that also can make have outliers in our data. So I started conducting transformations, and I did the look likelihood test to make sure, like, let's say for the sales price, it's close to zero, so I might as well try look transformation for this variable. And as you can see on the left side here, the sales price, the look sale price looks much better than the sale price, the original one, and also for the sample here, and it looks that look transformation fixed mostly the problem that we had in this variable. I did the same for the square foot area of the house and square foot area of the lot. And just to explain the difference between look value, lot is the whole lot of the house, and house as in number of stories and the area used for the house. So for the predictive analysis, I tried multiple models starting by one variable, multiple variables included, and different configuration of them. But the ones I settled in was two models, where model one was look square foot area of the house, look square foot area of the lot, full bathrooms, bedrooms, and division. And these are the results for this model as well as the residuals. And it really fixed a lot of the residuals, because before it was just cone shaped. By doing the log transformation, it fixed a lot of the problem. Model 2, however, just we add another variable, which is the metropolitan area. So whether this house is in metropolitan area or not, but the same variables as the first model. And division here is also related to the location characteristic of these projects. So where in the US these houses are. So we can also see here that the residuals are looking really good. The estimates, all these p-values are less than 0.05. They are all significant. And here for the interpretation, we are considering the look sales price to looks square foot area of the house. So that means with 1% increase in the square foot area of the house, the sales price of houses tend to increase by 0.94%. So, and the same goes for all the log variables and for also the other variables we have here. So I started comparing having model evaluation. We're comparing the two models by adjusted R square, log likelihood, AIC, BIC, and defiance. So the higher the adjusted R square, the better. So model 2, by just adding one variable, it increased from 0.618, which is 61.8% explanation of the variance of this model. It moved to 62%. So it is good to include this variable. For the log likelihood, the bigger, the better. So since we have both variables in negative, the lower the negative, which means it is bigger in value. So model 2 is still better. For the AIC, BIC, and defiance, the lower the value, the better for the model. So model 2 is performing better than model 1 in all aspects or all metrics evaluated here. I also did backcasting for model 1 and model 2. And as you can see, the line here fitted over the original data set that we have. And both of them looks very similar to each other, but since model 2 is still performing better in all metrics, I'm more inclined to use model 2 as my final model. And finally, the last thing is the cross validation. So you can see the root mean square error for model 1 and model 2 here, and model 2 is still lower in RMSE than model 1. So it is still consistent with the results of previous metrics that we had. So that's what I'm sitting on, is model 2. So for the conclusion, I conducted sales price prediction of single family house in the US, where the clean data were finally 30 variables, but not all of them were included in the regression model. I conducted exploratory data analysis, where the main thing I noticed is that I needed to make log transformation for the sales price, square foot area of the house, and square foot area of the lot, because they were highly skewed. And finally, for the build predictive models that I did in this project, I mainly focused on two final models, and the best performing model was model 2 with adjusted R square of 62%, which was much better than the model 1. So that is my presentation, and with that I concluded. Do you have any questions?